Next, we are going to discuss one very important topic under qualitative properties, that is osmotic pressure, osmosis and osmotic pressure. Okay. Let us try to understand what is this osmotic pressure is. Let us have two beaker. In this beaker, I have pure solvent, only pure solvent, and another beaker I have solution, and now these two beakers are connected by a tube, but in between there is something called semi-permeable membrane. Semi-permeable membrane. What is the semi-permeable membrane? It will allow the small solvent molecule to pass through, but it will not allow any solute molecule to pass through. So, here we have a pure solvent, here we have a solution. So, this side we have some solute molecules. So, that will not go through. So, here it will always remain pure solvent. Only solution, the solvent molecule can pass through from this semi-permeable membrane, and then we will see the rise. There will be some solvent molecule passing through from this side to this side, and then there will this side will go down and this side will rise, and this change in height, which can be directly related to the pressure, and that is called osmotic pressure. Okay? And this again I can apply a pressure over here such that the the height becomes same on both sides. That pressure has to be equal to the osmotic pressure, and this osmotic pressure is experimentally verified. It is equal to, the osmotic pressure is equal to concentration, this is molarity, gas constant multiplied by temperature. This is a very important quantity. This is exactly used to get clean water by reverse osmosis. That is, if I apply pressure more than the osmotic pressure, then I can transfer solvent, which is going to go through the semi-permeable membrane to other side, and this side we will have only pure solvent, drinkable water. Okay. And but it has a lot of technological importance also, as we have seen. If I have a 0.1 molar solution, if I have a 0.1 molar solution, then the change in boiling point is going to be delta T is going to be kbm, and that kb is around 0.5. So, delta T is going to be approximately 0.05 degree centigrade, very small change in boiling point. But what about this? Let us see. Okay, I can assume in this case this is a very dilute solution. So, 0.1 molar is approximately equal to 0.1 molar. Okay, let us look at the definition of molality. Molality is moles of solute divided by weight of solvent. What is molarity? Molarity is the moles of solute divided by volume of the solution. So, if we assume 1 liter solution, a dilute solution has a more or less 1 kg of weight, which is a fairly good assumption for water. In that case, molality and molarity is going to be same. Now, so 0.1 molar at room temperature is going to be approximately 0.1 molar is going to be approximately 0.1 molar. So, for 0.1 molar solution, delta T, the change in the boiling temperature is 0.052, but in case of osmotic pressure, let us calculate it. So, for 0.1 molar solution, this is going to be 0.1 multiplied by, let us assume the temperature is around 0 degree centigrade. So, this RT is 22.4 liter ATM. So, I am going to get 2.2 ATM change in pressure. That is huge. It is easily measurable. That is more than the twice of the pressure exerted by atmosphere. You see that this is 0.05 for 0.1 mole and this is 2.2 ATM. So, this quantity, this osmotic pressure becomes very important when we are trying to calculate the concentration or molecular weight of in a biological system where the molecules are huge, very big, they have a very large weight, but the concentration is quite small, because the moles, maybe 1 mole might have a thousands of gram weight. So, when the concentration is very small, still let us say concentration is like a millimole and even smaller, we are delta T is going to be negligible, but we still can get appreciable change in osmotic pressure, and that would be very useful to calculate the concentration, or if we know the concentration, then the molecular weight of these biological proteins and things like that. Okay, let us do an example. 200 centimeter cube of an aqueous solution of a protein contains 1.26 gram of the protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2.57 into 10 power 3 bar. Calculate the molar mass of the protein. Let me read out one more time. 200 centimeter cube of an aqueous solution. Volume is 200 centimeter cube, that is 0.2 liter. Contains 1.26 gram. Mass of solute is 1.26 gram of the protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2.57 into 10 power minus 3 bar. Calculate the molar mass of the protein. Okay. So, we are given pi, this is exactly here, C is the concentration. Okay. The concentration over here is a molar concentration. So, that is defined as moles of solute divided by volume of the solution. So, I am going to assume that since the concentration is going to be extremely low, so volume of the solute is equal to the volume of the solution. So, we are going to get this quantity 0.2, molecular weight N2 is simply weight of the solute 1.26 gram divided by molecular weight of the solute. So, that is the unknown quantity. So, we plug in all this information and we get 1.26 W2 into 0.2 is equal to are in a proper unit. So, I need this in a bar unit, and that is going to be 0.083 liter bar per mole per Kelvin into temperature, that is 300 Kelvin. So, only unknown is W2. So, let me rewrite it. So, W2 is going to be 1.26 into 0.083 into 300 divided by 0.2 into 2.57 into 10 power minus 3. So, if I plug in all this information, I am going to get W2 as 61,022 gram per mole. Okay. So, this is a huge protein molecule. Now, I will leave it as an exercise for the viewers, that if for the same solution, if I ask to calculate the change in freezing point and boiling point, it is going to be really negligible and won't be able to probably measure it experimentally. Okay, let us do another problem. At 300 Kelvin, 36 gram of glucose present in a liter of its solution has an osmotic pressure of 4.98 bar. If the osmotic pressure of the solution is 1.52 bar at the same temperature, what would be its concentration? At 300 Kelvin, so temperature is given, temperature is important. For osmotic pressure at 300 Kelvin, 36 gram of glucose. So, weight of solute is 36 gram, is present in 1 liter. So, volume is 1 liter, has a osmotic pressure of 4.98 bar. If the osmotic pressure of the solution is 1.52 bar, then what is its concentration? Okay. So, in this equation, pi is equal to CRT. So, 4.98 bar is equal to C is 36 gram divided by molecular weight of glucose, that is C6H12O6. So, 72 plus 12 plus 96. So, 10, 180 in 1 liter RT. Now, is asking if 1.52 bar is osmotic pressure, then what is concentration? Okay, looks like this information has no value, not required. So, C is simply given by 1.52 divided by 0.083 into 300 Kelvin, and the answer would come out to be divided by 0.083 divided by 300, 0.06, 0.061 molar. Okay, let us discuss now abnormal molar masses. Okay. So, we have seen using the qualitative properties, we can calculate molar mass. For example, using delta T of boiling. Using this equation, we have calculated molar mass of solute, but we have been talking about non-ionic solute. What about ionic solute? What happens if solute goes into the solution and it might dimerize or it might dissociate? For example, if I take NaCl, put it in a water, it is going to dissociate to Na plus aqueous plus Cl minus aqueous. If I took 0.1 molar solution to begin with in water, then this being a very strong electrolyte, it is pretty much going to, let us assume it is going to dissociate completely, and we are going to get 0.1 molar Na plus and 0.1 molar Cl minus, and nothing will left. That is an assumption, fairly good one. Okay. And we know the colligative property does not depend upon what solute you are using. It depends on simply the concentration of each and every individual solute added up. So, to calculate colligative properties, now we have 0.1 molar Na plus, 0.1 molar Cl minus, and total concentration which is going to go into this equation is going to be 0.2 molar. If for example, it dissociate only 50%, we know it is not going to dissociate, it is going to dissociate much more, but let us assume that it is going to dissociate only 50%. Then out of 0.1 molar NaCl, what is left is 0.05 molar NaCl, and remaining will convert into Na plus and Cl minus, 0.05 and 0.05. So, the total concentration molality which is going to get into this equation is going to be, you add these three individual quantities. So, in solution NaCl is present, Na plus is present, Cl minus is present. So, for this equation it does not matter what is present, it just want the concentration of all the solute present. So, the total concentration is now going to be not 0.1 molar, but 0.15 molar. If we can define the degree of dissociation, for example, if degree of dissociation is alpha, then 0.1 into 1 minus alpha will remain in the solution, and rest will convert into in this Na plus and Cl minus, and that would be 0.1 alpha and 0.1 alpha. So, the total concentration is going to be, simply add up these three quantities, and that will go to this, and using, if I know delta T, if I know Kb, and if I know how much NaCl I added to begin with, I can calculate degree of dissociation. That is a very important quantity. Not only dissociation, sometimes we can have a dimerization. We have some compound which put into the solution and it might dimerize, it might polymerize one. So, in that case, if I start with concentration of N and degree of polymerization is alpha, then what is left is N 1 minus alpha, and how much A2 we are going to get is, so out of N moles, N alpha moles has converted to A2 and giving rise to N alpha by 2 moles of A2. So, when calculating the total concentration, the amount, the moles which is going to go into the calculation is this plus this. So, in this case the concentration has gone down. For example, now if I have a general compound, let us say AMBN, the concentration is C, degree of dissociation is 1 minus alpha, sorry, degree of dissociation is alpha, then this compound which will remain in the solution is this much, and we are going to get A ion, that the concentration of that ion is going to be C alpha m, and the concentration of B ion is going to be C alpha n. So, the total concentration is going to be this plus this plus this. Okay, let us do some exercise to understand this concept. So, this is example 2.12. Let me read. 2 gram of benzoic acid is dissolved in 25 gram of benzene, shows a depression in freezing point equal to 1.62 Kelvin. Molar depression constant of benzene is 4.9 Kelvin kg per mole. What is the percentage association of acid if it forms dimer in solution? Okay. So, we are given 2 gram of benzoic acid. So, that is solute. So, weight of solute is 2 gram benzoic acid, that is C6H5 COOH dissolved in 25 gram of benzene. So, that is solvent. So, it dissolved in 25 gram of benzene. Shows a depression in freezing point equal to 1.62 Kelvin. So, delta T is 1.62 Kelvin. Molar depression constant for benzene is Kf is 4.9 Kelvin kg per mole. What is the percentage dissociation of acid if it forms dimer in a solution? So, this benzoic acid in the solution is going to give me C6H5 COOH twice of that, and not all of it is going to be dimerized. So, is asking what percentage is going to dimerize or and percentage association. Okay, so percentage is asking. Okay, so we will start with our familiar equation. So, that is delta T is equal to, this is a freezing point. So, depression, so this is Kf m. Kf is given right here, and we need the molality of all the species present. The species which are present is C6H5COH and its dimer, benzoic acid and its dimer. So, we started with 2 gram. To calculate the molality, we need to convert this 2 gram to moles of benzoic acid. So, we need the molecular weight. So, molecular weight is going to be 7 carbon. So, that is 84, 6, 90 plus 32. So, 122. So, we get moles of benzoic acid as 2 divided by 122. And then we are going to have some dimerization. So, percent dimerization, let us say the degree of dimerization is alpha. So, we are going to get 1 minus alpha, and we are going to get this dimerization 2 by 122 alpha. That many benzoic acid dimerized, and the concentration of due to dimerization is going to be half of that. So, the total concentration is going to be this plus this. Okay, I am sorry, we still need to calculate the concentration. The number of moles of benzoic acid present in the solution is going to be this, and moles of dimer present in the solution is going to be this. So, we are given weight of the solvent. So, the molality, the total molality of both the species, both the solute is going to be, just add it up. So, we are going to get 2 divided by 122, 1 plus 1 minus alpha plus alpha by 2. So, this is the moles divided by 25 gram, and that we need to convert into kg. So, just multiply with 1000. 0.661 minus alpha by 2. So, that is going to be the molality. So, now we have all the information, we need to just calculate alpha and just multiply by 100, that will give me percentage association. So, delta TF 1.62 Kelvin equal to 4.9 into 0.661 minus alpha by 2. So, we are going to get 1 minus alpha by 2 as 1.62 divided by 4.9 divided by 0.66, 0.500. So, alpha by 2 is going to be 0.500. So, alpha is going to be 1. So, this is a nearly 100% association. So, nothing will remain, practically nothing will remain of this, everything will convert into dimer if I put benzoic acid in benzene. Okay. Let us do another problem, the next exercise. Okay, let me read it out. 0.6 milliliter of acetic acid having density 1.06 gram per milliliter is dissolved in 1 liter of water. The depression in freezing point observed of this strength of acid was 0.0205 degrees centigrade. Calculate the want-hour factor and the dissociation constant of acid. Okay, let me first define what is want-hour factor is. So, want-hour factor is concentration of the species present in the solution, let me call that experimental concentration, and divided by theoretical concentration. Theoretical concentration is the concentration which I am calculating, that is the concentration before any reaction happens in the solution, that is any dissociation or polymerization happens. So, that is the concentration, theoretical concentration. Okay. And this concentration can be in a molality, it could be in a molarity, whichever way you want. So, if I am trying to calculate say osmotic pressure, pi is equal to CRT. So, if I substitute C as a theoretical, then pi is going to be the calculated one, and if I substitute C as the experimental, the actual concentration present in the solution, then it will be experimental one. So, it is clear to see that this is basically going to be pi experimental by pi theoretical. Or if I am calculating, let us say freezing point depression or boiling point, then delta T is again Kb by m. This is a molality, and again we are going to get. So, if I substitute theoretical concentration, then I am going to get what delta T I calculate by putting the concentration which I am using, or experimental would be, or the experimental change in temperature would be using the molality of the component present in the solution. So, again I can substitute concentration equal to delta T by Kb, Kb will cancel out in both ways, and again I will get delta T experimental and delta T calculated or theoretical. So, you can see want-hour factor is simply experimental colligative properties, divided by calculated qualitative properties. So, that is how the Van 't Hoff factor is defined. So, for example, if NaCl is going to dissociate completely, then one NaCl is going to give me two species, one Na plus and another Cl minus. So, my experimental concentration would be twice of theoretical concentration. So, Van 't Hoff factor in case of NaCl is going to be 2 if it is going to dissociate completely. Okay. So, the problem which we are going to attempt is asking to calculate Van 't Hoff factor. Okay. So, in this problem we are given 0.6 liter of acetic acid, having density it dissolved in 1 liter of water. So, volume of solvent is 1 liter. The depression in freezing point delta Tf was observed to be 0.0205 degrees centigrade. Calculate the Van 't Hoff factor. So, we need to calculate I and dissociation constant for the acid Kb. Okay. So, dissociation constant of Kb is defined as follows. So, first let me write the reaction. Acetic acid, that is CH3COOH, when it goes into water, it is dissociates and gives me acetate ion and H plus. Of course, it is an acid, it has to give H plus. Okay. And so, the Kb is defined as concentration of H plus, concentration of acetic ion divided by concentration of CH3COOH. And the concentration unit which is used here is molarity. Okay. And we need to use this equation also, that is defined as Kf multiplied by m. So, this is molality. So, but in this problem we are going to consider molality and molarity happen to be same. Why is that? We are going to consider that 1 liter water is equal to 1 kg of water. And if I add 0.6 ml of acetic acid, it is not going to change the volume of solution. So, we are going to assume 1 liter of water is equal to 1 kg of solvent, and that is equal to 1 liter of solution. So, if I am going to calculate the concentration, that would be moles of solute. So, that is weight of solute, that we can calculate by volume of solute multiplied by density. So, the weight of solute is 0.6 into 1.06 divided by this is the weight of solute, and if we divide by molecular weight of solute, that would be 12 or 24 plus 4, 28 plus 32, 12, 15, 20, 60. So, weight of solute divided by molecular weight, that is moles of solute divided by weight of solvent. Since we are assuming 1 liter water is equal to 1 kg of water, so we can divide by 1 kg. So, this will give me molality. And if I want to calculate molality, I again have assumed that 1 kg of water or 1 liter of solvent, if I add solute to it, it is not going to change its volume. So, instead of 1 kg, I use 1 liter and I again get the same answer. It is simply 0.6 into 1.06 divided by 60. I can either molality or molarity. It is the same number. So, I am going to get 1.06 into 10 power minus 2, molar or molar, it does not matter. So, we have calculated the concentration. If degree of dissociation is alpha, then if the initial concentration was C, which is right here, and degree of dissociation is alpha, then C multiplied by 1 minus alpha, that much acetic acid will remain in the solution and remaining part will dissociate and is going to give me C alpha of acetate ion and C alpha of H plus ion. And if I take that all that information and put in right here, I am going to get C alpha square divided by C 1 minus alpha. Okay, and where C is given right here. Okay, so we need to calculate Kb, we need to calculate I. So now the total concentration which I am going to use while calculating the qualitative property, that is going to be concentration of all the individual components in the solute. So, all these three are solute in the solution. So, the total concentration is simply going to be this plus this plus this, and that is going to be C 1 plus alpha. Okay. So, I have now all the information. I just need to calculate alpha. Since I know C, if I know the alpha, then I can calculate the Kb. And of course, I can calculate I also, the want of factor, and that would be the experimental concentration, that is this concentration, that is after dissociation, and the concentration before dissociation, that is C. So, it is simply 1 plus alpha. So, I just need to calculate alpha and I will have all the answer I require. Okay. So, I am just going to plug in all the information in this equation. So, for this I of course need Kf, and Kf is given in the table, and if I take it from there, it is 1.86 Kelvin kg per mole, 1.86, and the molality is, we have already defined C, that is 1.06 into 10 power minus 2 multiply 1 plus alpha. And now I can calculate 1 plus alpha. That is going to be 0.0205 divided by 1.86 divided by 0.0106, and answer is 1.0397 or 1.04, 1.0397. So, alpha is going to be 0.0397. So, want of factor we have already calculated, that is 1.0397. Now, what about Kb? So, if I put all this information, 1.06 into 10 minus 2 alpha square, that is 0.0397 7 square divided by 1 minus alpha. So, 1 minus 0.0397. Let us see what answer we get. So, okay, the answer which we are going to get is 1.74 into 10 power minus 5. So, within round of error, this is, I think, is the answer. Okay, let us discuss one more problem from the text. This is 3.32 from NCERT book. Calculate the depression in the freezing point of water when 10 gram of CH3, CH2, CHCl, COH is added to 250 gram of water. So, he is asking calculate the depression in freezing point. So, he is asking delta T F when 10 gram. So, weight of solute is 10 gram and the solute is CH3, CH2, CHCl, COOH. So, 10 gram of this is added to 250 gram of water. So, weight of solvent is 250 gram and we are given Ka is equal to dissociation constant for this acid is 1.4 into 10 power minus 3 and Kf for water is 1.86 Kelvin kg per mole. Okay. So, we need to calculate depression in freezing point. The usual formula is going to be Kbm, and where is the molality of all the component present. Okay, just for the simplicity, let me write this as A. So, this whole compound is simply Ha, which is going to dissociate and going to give me H plus A minus in solution. And again, if the concentration, the theoretical concentration is C of Ha, then after dissociation, if the degree of dissociation is alpha, then after dissociation the concentration of Ha will become C multiplied by 1 minus alpha, concentration of H plus will become C alpha and concentration of A minus will become C alpha. So, now I can write Ka, which is defined as concentration of H plus multiplied by concentration of A minus divided by concentration of Ha. We can write this in terms of C and alpha. So, concentration of H plus is C alpha, concentration of A minus is C alpha and concentration of Ha is C 1 minus alpha. So, putting it and removing one C, we are going to get C alpha square divided by 1 minus alpha. Okay. Now, let us try to calculate C, that is the concentration of the solute in the solution before dissociation. So, C is if we want to write in molarity, then it is going to be moles of solute divided by weight of solvent in kg. But we are going to consider the molality and molarity to be same, because we are going to assume the weight of solute weight of solvent is 0.250 gram and the volume of the solution is also 0.250 liter. So, in that case the concentration in terms of molality or molarity is going to be same. To calculate the concentration, we need a molecular weight of this compound, and so the molecular weight of this compound is going to be 15 plus 14 plus 13 plus 35.5. This is 12 plus 113 plus 30 to 45. So, this would be 35 plus 45 80, 80 plus 1529 plus 1342 and 0.5. So, this is 122.5. So, molecular weight of this compound is 122.5. So, moles of solute N2 is simply 10 by 122.5. So, I have all the information now to calculate C. So, this would be 10 divided by 122.5 divided by weight of solvent, that is 0.250 kg. Kg, and if I just evaluate this, 0.3265. 0.326, and now I need alpha to so this information I am going to put it in this equation. So, I will get 0.326 alpha square divided by 1 minus alpha. So, this is to solve quadratic equation, but let us see if we can make approximation. Let us first make approximation. Alpha is negligible with respect to 1. In that case, alpha is simply 1.4 into 10 minus 3 divided by 0.326 and square root of that. So, the answer is alpha is equal to 0.0655. So, we ignored 0.0655 with respect to alpha. So, if you want to refine this solution, we are just going to substitute this alpha in the denominator, recalculate alpha. This is a very nice method to, if you do not want to solve this quadratic equation, or if some cases even a higher order equation, I can do it iteratively. Just make approximation over here, calculate alpha, and whatever alpha you get, just keep on substituting here, and couple of iteration, most probably it will converge. Many times diverge also, but I have seen most of the time it converge. So, just replacing back this. So, I am going to get K A is equal to 0.326 alpha square divided by 1 minus alpha, that would be 0.9345. And now, using this equation where K is given here, I will get 633. So, alpha is simply 0.0633. So, it is quite close. All right. So, we have calculated alpha. Now, we need to calculate delta TF, where M is going to be the total concentration of all the species. In all the species which are present is H A, H plus A minus. So, if I add up the concentration, the M is simply going to be C multiply 1 plus alpha. So, if I put all the information here, Kb is given, I am sorry, this is Kf. Kf is given is 1.86 multiply by C, which is we have already calculated somewhere, that is 0.326 multiply by 1 plus alpha, alpha is 0.063, 1 plus alpha is 1.0633. And now, we can calculate delta TF is going to be 1.86 multiply by 0.326 multiply by 1.0633, and answer is 0.645. So, change in freezing point is going to be 0.645 degree centigrade or degree Kelvin. If one want to calculate Van-Taw factor, then that also we know, it is simply 1 plus alpha. So, Van-Taw factor is 1 plus alpha, which we have discussed in the last class, and that is equal to 1.0633. Okay, let us try to solve one last problem in this session. Okay, the next problem. 19.5 gram of CH2FCOH is dissolved in 500 gram of water. The depression in freezing point of water observed is 1.0 degree centigrade. Calculate the want of factor and dissociation constant of fluoroacetic acid. Okay, this is a very this is quite similar to the problem which we have discussed earlier. Okay. So, 19.5 gram of this acid. So, weight of solute is 19.5 gram, and the solute is CH2F COOH. Dissolve in 500 gram of water. So, weight of solvent is 500 gram. Depression in freezing point is water is observed to be 1.0 degree centigrade. So, delta TF which is observed is 1.0 degree centigrade. Calculate want of factor I and the dissociation constant Ka. Okay. Again, if I write this whole equation, dissociation of H A giving me H plus A minus, where I am assuming this is A. Then, if initial concentration is C, undissociated concentration, and after dissociation degree concentration is going to be 1 minus alpha, then the concentration of H plus is going to be C alpha, concentration of M is C alpha. So, total concentration of each and every species is going to be C 1 plus alpha. So, want of factor, as we have already discussed, is going to be C 1 plus alpha divided by C, that is 1 plus alpha, and Ka is going to be concentration of H A multiplied by concentration of A minus divided by concentration of H A, that is C 1 minus alpha. So, that would be alpha square C 1 minus alpha. Okay. And we can calculate C. So, C is going to be molality or molarity. Again, we are in this dilute aqueous solution, molarity and molarity we are going to assume it to be same. So, we are given mass and we want to convert it to moles. So, to convert to moles we need a molecular weight. Again, molecular weight of this compound is going to be 14 plus 9 plus 12, 13 plus 13, 45. So, 4, 9, 18, 1, 2, 3, 78. So, molecular weight is 78. So, the concentration is moles of solute. So, that would be 19.5 gram divided by molecular weight, that is 78, divided by either volume of the solution which we are considering equal to the volume of solvent or weight of the solvent. So, that is to calculate molality. So, that is 0.5. So, this is 19.5 divided by 78 into 0.5, 0.5. So, this is this comes out to be 1 by 2. So, simply 0.5 molal or molar. Okay. So, we have C and we already given TF. So, delta TF is KFM, where M is the total concentration of all the species, that is C multiply 1 plus alpha. So, this is going to be Kf into C 1 plus alpha. Kf is given the last problem itself. So, we can use it 1.86 multiply by 0.5 multiply by 1 plus alpha. Okay, so, we can calculate 1 plus alpha equal to 1.0 divided by 1.86 into 0.5. So, 2 divided by 1.86. Okay. The problem in these questions, in this exercise, is how many significant figure to carry. So, okay, let me carry just 1.075 as 1 plus alpha. So, alpha is becomes simply 0.075. If I carry just 2 significant, I will not get any answer. So, alpha is 0.075. So, we already have the want of factor is simply 1.075, and Ka now it is straightforward. C is we have already calculated, that is 0.5 into 0.075 square divided by 1 minus alpha, that would be 0.925, and now we can calculate this trivially. 0.75 square. So, 3.0 into 10 minus 3. So, that is what we get the dissociation constant for this acid. Okay. So, that is where we will stop this session.